Welcome back to the Lowdown on Physics. This is Screencast number 13 in the series on VCE Unit 3 Physics, Motion in 1 and 2 Dimensions. Today we'll be looking at energy changes in gravitational fields. Let's start by looking at what we know about energy and gravity and work and apply that to scenarios involving satellites. To start with, we know that any object that experiences a force due to gravity and moves through the gravitational field will have work done on that object. As a result, there will be a change in kinetic energy that is equal but opposite to the change in gravitational potential energy. When we are close to the Earth's surface, we approximate that by mgh, mass times acceleration due to gravity times the height that it moves through. Now consider a satellite that's in a circular orbit. Because the distance between the satellite and the Earth, or whatever it's orbiting, would be constant, that means the gravitational potential energy would be constant. That also means that the kinetic energy would be constant because the force would always be perpendicular to its motion, so it wouldn't change its velocity. And as a result, no work is done. Now, most satellites, natural and artificial, don't actually move in circular orbits. The majority of them will move in elliptical orbits. Now, as a result, because they are travelling at different distances, then we're going to experience a change in the gravitational field strength, and there will be changes in speed, so kinetic energy, and because of the change in distance, there will be a change in gravitational potential energy. So consider the following object that is in orbit around the Sun. Let's have a look at what happens to the force that's acting on it at these given points. At this point here, force is perpendicular. However, force will be on an angle. Okay, so then the force due to gravity is going to result in changes in the gravitational potential energy. Force here again will be perpendicular, and then as we get here, force pulling it back in towards the Sun. So at this point here, it's speeding up. Does the total energy of the satellite change at any given point? So the key word here is the total energy. And the answer's got to be no, okay? So the energy will be accounted for, it will change from one form to another, but we don't actually lose or gain energy. So how do we actually go about calculating the work done on a satellite when it's in an elliptical orbit? What you can see from this graph here is that as you move away from the object that you're orbiting, that G is going to change dramatically the further you get away. So we don't have constant G, so we can't use mgh. So what we can do is we can calculate the work done. So effectively we're going to have a distance force graph. On a distance force graph, the area under the graph is the work done. So we can analyse and approximate an area under the graph for a change in distance. As it moves closer, the work done results in an increase in kinetic energy and a decrease in gravitational potential energy. As it moves further away, then it's going to get greater gravitational potential energy but decrease in its kinetic energy. Let's look at an example. So we have a 1 kilogram object and it moves a total of 6,390 kilometers from the surface. So you would calculate area under the graph. In your exam, an approximation is what you're going to be looking at. So you're going to be counting the number of squares. You know, if it's approximately a triangle, then you can approximate a couple of triangles, a couple of rectangles, and calculate it that way. Or just best guess on how many total squares there would be and multiply it by the values that each square is worth, how much it is worth going up, how much it is worth going across. Now, important important to note is this axis here. Okay, this is G. Shows you how G changes as distance changes. Since we have a 1 kilogram object, the force would be G times 1, mg for weight force. So what would we do if we had a 25 kilogram object? You would have to multiply the value of the area under the graph by 25 to make this force. Okay, so you could multiply this axis by 25 and do the calculation that way, either way. But you do need to be aware, sometimes they will give you a force axis here, sometimes they will give you G. So have a look and make sure you know what axes you're working with. Don't just go on autopilot. It's a common trick that they do use. Okay, another example. We've got an asteroid, 500 kilograms, heading towards the moon. We have a speed of 250 meters per second when it is this distance out from the moon. We're also given the moon's radius. So what we're going to do is analyze that as it crashes. Check out that animation. That was sick. So to do that, we need a graph displaying that information. So calculate the kinetic energy first up. So we have a half mv squared. We know mass was 500, and velocity was 250. So a half mv squared. We have a total of 15.3 megajoules. Calculate the increase in kinetic energy now. So what we need to do is look at the amount of work done, which is the area under the graph. Now in this scenario, probably the most accurate way is to look at the number of squares and then multiply by the value of each of these axes. So here I calculated it to be about 53 squares, but I'd encourage you to have a go and see how close you come to that figure. So I'd count all the whole squares first, then I'd start looking and saying, well, that one there is approximately one more square. Those two there would be another square, and so on, and see where you come up with. You may come up with a half a square or a whole square different to me. So there's a bit of leeway on these approximation calculations. Once you've got your number of squares, multiply it by the value. So these are 0.1 times 10 to the 6, and then these values here are 100. So multiply the total number of squares by the total area for one square to find the area under the graph. So I've got 530 megajoules of energy. That's the increase, or the work done, and that's going to result in the increase in the kinetic energy. So part C says find the speed when it hits the moon. So what we need to do is we need to look at the total energy, or the total kinetic energy at the point of impact. So it's all of the increase in kinetic energy plus the kinetic energy it had before. That equals a half mv squared. So if we sum those together, we divide by a half times the mass of 500, and then we take the square root. We get about 1,477 meters per second, the velocity at the point of impact. Double check that calculation because I did it pretty quickly, so I may have punched into the calculator wrong, but it does sound like a reasonable value. Okay, find the gravitational field strength 500 kilometers above the surface. So we need to look at 500 kilometers above the surface. So we're talking 1, 2, 3, 4, 5, and then up. We've got a force of 500 newtons acting on the asteroid at that point. So 500 newtons when we go 500 kilometers above. We get, if that's a force of 500 newtons, then G equals F over M. Force divided by mass, we've got 500 divided by 500. We've got 1 Newton per kilogram, that should read, or 1 meter per second squared. So that's it for energy changes, and in fact that's it for motion in 1 and 2 dimensions. So give yourself a pat on the back. We have reached the end of the first topic for Unit 3 Physics. I'll see you in class shortly and we'll start hitting up some heavy revision.